Welcome to a new series on demystifying finance mathematics. I'm going to be taking you through some core concepts that you need to understand portfolio management and risk management. We're going to go through common misconceptions and lay the foundational groundwork that you need to understand all of this in a step-by-step manner in a course-like structure. Now, anticipating this, I've already gone ahead and made a little list of notes of topics that I think are going to be of interest. I'll go through them, and if these intrigue you, stay around. I want to start with what I'm calling Type 1 concepts. These are your basic, fundamental finance mathematics ideas that we need to go through to set the foundation in place. Here we're going to talk about standard deviation, expected returns, correlation, covariance, and basic metrics like Sortino and Sharpe Ratio. We're also going to be talking about some basics of statistics like the normal distribution, skewness, and kurtosis. Now, combinations of these ideas are going to build into Type 2 ideas here. This is volatility, time horizon, risk factors, risk budgeting, fat tails, value at risk, and extreme value analysis. We're also going to be looking at what proper diversification is from a mathematical point of view. If you've ever heard rule of thumb suggestions such as get your stocks in as many different sectors as possible for diversification, that's only partially true. Diversification is really a mathematical concept, and we're going to dive into that in this part when we hit Type 2 concepts. And then selections of Type 2 concepts are going to build into high-level tools or frameworks. This is where we get into the interesting territory of efficient market theory, modern portfolio theory. We're going to go through tactical asset allocation, efficient frontier, and by the time we hit this, we will have put in place all of the foundational work you need to understand why these concepts are important and how you can apply them to your portfolios and your investing. And I want you to know I'm coming at this not from a financial advice point of view. I'm not trained in finance, but I am an engineer, a data scientist, and a statistician. So all of this work is purely focusing on the quantitative and mathematical side of finance, giving you that understanding for you to take these concepts and apply them as you like for your own use cases. So, without going further, entry point number one for us is going to be expected return. Now, for some of you, this might seem very boring. Some of you might think you know what this is and won't actually, and we'll test that real quickly. So, jumping straight in, expected return. There's really two kinds here, arithmetic means and geometric means, right? You may also see log returns thrown around when you're reading articles or watching videos. Well, log returns are a thing. Log returns are a type of geometric mean. They're geometric means taken to their logical conclusion, but that gets a bit mathematical, and that's not what we're going to be focusing on this kind of content. So for now, we're just going to stick with these two kinds, arithmetic and geometric, and talk about the difference. So here we go. What is the difference? What are they? For the arithmetic mean, you simply add up a series of returns over some time period and then divide by however many time periods you had, however many returns you added up. It's a simple average, right? It's really easy to do on the back of an envelope in your head. So let's go through these examples. So imagine that you have been investing for a whole year, January through January, and you look at your performance and you've had a return of 12% by the end of the year. And you want to try and understand where your portfolio might be in an additional 2 months' time. How would you go about that? So what you might do is say there's 12 months in a year, I had a 12% annual return. So if I divide that by 12, that's 1% for each month, 1% each month, 12 months, 12% return. That would be an example of working out the arithmetic mean. Now, you can do that, but it's not quite right. It'll get you an answer that's kind of close, especially if you're only forecasting a small distance into the future. But generally speaking, this gets pretty inaccurate pretty quickly. I'll show you what I mean. Looking at some real world examples here, Microsoft and Apple. Here we have Microsoft in blue and Apple in orange. Here's the historic price chart, and looking at a specific section of this that's shaded under the graph, we'll be looking at the percentage difference day to day and then working out based on those percentage differences from day to day of these close prices, what happens if we do a forecast all the way from the beginning of the shaded region all the way to the end using the arithmetic mean of those percentage differences and the geometric mean. Now I know we've not been through what the geometric mean is yet, but bear with me. For Microsoft here, the green dotted line is a forecast based on the arithmetic mean. The red line is for the geometric mean, and you'll see the arithmetic mean is very optimistic. It massively overshoots the actual endpoint of the time period, whereas the geometric mean lands very nicely where it should do. Likewise for Apple here, this purple dotted line is based on the arithmetic mean. It overshoots the ending value. It's optimistic, whereas this grey dotted line here is ending exactly where it should be. That's the geometric mean. Okay, so arithmetic mean, it's simple to work out, but it's not quite accurate. It's too optimistic. What's the geometric mean? How do we work this out? Well, going back to that analogy of the 12% at the end of a year, to work out what your monthly geometric mean would be, you take your 12% and you take the 12th root. You can do this on Google. If you have a Casio calculator, you can do it on something like that. But this is the important bit. You take the 12th root and you get this value here, which is 0.949%, slightly less than 1% from the arithmetic mean. But that slight difference is important because as you compound this over a longer and longer time horizon, the difference between the arithmetic mean and geometric mean keeps growing. So here we're going to our little example. This is a 12-month period from 2024 January to 2025 January in this hypothetical. This yellow dotted line would be a projection using your arithmetic mean, that 1% per month. If we actually compound this on a monthly basis following this step graph here that comes and meets this yellow line, you can see that we end up actually at a point 113 beginning at 100, closer to a 13% return. That's interesting. And then the geometric mean, we do the exact same thing and we end up at bang on 12%, which is great. And you can see as each month goes by, that tiny little percentage difference compounded leads these steps to get further and further apart. So that's what you've got to be aware of. Over short time periods, it's not that big of a deal. You can use the arithmetic mean for a back of the envelope calculation for a short time period, or if you're not that interested in the accuracy of your final result, you just want a ballpark figure, it's absolutely fine. But when you're doing rigorous quantitative work, you've got to use the geometric mean. So with all of this information, how would you apply this to a real world example? Okay. We have here the trading balance of a trader over the course of 5 years. We have the monthly breakdowns in returns as percentages. We also have the annual breakdown on this total column on the side. So let's look at this. Just looking at the year by year returns, we have this list here. Now, here's how you would work out the arithmetic mean. You just add up all of the percentages and you divide them by however many years there were, in this case, 5. And if you do that, you get 20.82%. That would be your arithmetic mean. But the geometric mean is a bit more complicated. For the geometric mean, we've got to go from addition to multiplication. And to do that, we've got to move from percentages to growth factors. The way you do this is you take your percentage, you divide it by 100, and then you add 1. And that will result in these growth factors given the percentages year by year. To make the geometric mean, you just multiply them all together. This fancy maths term here, this big pi symbol, kind of looks like a table, that means multiply all of these together, and this r in this equation means what you're doing is you're taking your percentage here, ri, dividing it by 100, adding 1, that's all of these numbers right here, and then you just times them all together. And then you take the nth root that we mentioned earlier. So we do this, multiply them all together, take the 5th root, that will give us something like this, a growth factor, -1 to get back to a percentage, 15.68%. It's much more conservative, but that's because it's taking into account the compound growth. So if we now do our forecast an additional 2 years into the future for this particular trader, here's what you do. The arithmetic forecast looks like this. We plug it into the standard compound growth formula that we all know. Here we go. 1 plus that. 20.82 over 100. That's our 20.82% growth rate from the arithmetic mean. Squared here to the power of 2 because we're forecasting 2 years into the future, and we get 45.97% return predicted for the next 2 years. However, if we use the geometric mean, 33.84%, that's more than a 10% difference in return. So hopefully that's explained the different types of expected return, the difference between them, and why you've got to be sure of which one you're using, particularly when it comes to mathematical work and forecasts far into the future. All right, so it's simple. Hopefully that's taught you a little bit about expected returns. You might have known this already, but this is the groundwork that we need to move on to the more exciting topics. All of this is going to build and build and build, and eventually we'll end up at the efficient frontier and tactical asset allocation, which will be really exciting because then we can really talk about how to build a portfolio for investment for the short and long term. All right, tune in for the next one. Bye.